calculating pressure in static fluids. So here I'm going to present several examples to try to help you as a student be able to understand in particular what the pressure is at a particular depth within a fluid. And we're going to take a look at several examples. The containers will change. I'm going to throw in both the atmospheric pressure into the mix. I'm going to talk about the absolute pressure, which is the summation of atmospheric pressure, and then the gauge pressure, which you can see there on the screen, the actual formula for. Now we're going to be diving into numerous cases within. It does not matter what the fluid that you are studying or the combination of fluids that you are studying, but for every fluid, as you may know, each fluid will have a different density. So, you can certainly run in, as you can see there on the bottom left corner, to various densities. Now, the most common one, okay, which might be water, but there are certainly other ones. For example, mercury, if you're going to be a student of health sciences, for instance, you're interested in blood pressure, then all of this, okay, with regards to mercury may eventually help you because of the fact that you might be able to think about those measurements of blood pressure in general. But in this instance, I'm not calculating, any blood pressures. I am just talking about the general fluids. And for the sake of this video, most of the time I will just simply concentrate on water as being the fluid. But it does not have to be, right? Please remember, fluids doesn't mean that it's an actual liquid. It could also possibly mean that it's a gas. And gas, like air, is the most common one because you see it right in the equation here, which is the atmospheric pressure, which is coming from the atmosphere, which is the air around us. So let's dive in here and try to break these things down. So let's start, okay, so here, okay, number one, on the left-hand side, let's kind of go back and review the concepts behind understanding what the pressure is at a particular depth. Now, in order to do that, what I'm going to do is I'm going to kind of draw a line in here, which is going to cut through all of these different containers that you see. So I am going to, draw a line all the way through. And as you can see here, because the containers have the same exact height, and let's say it's water, okay, that is the fluid, the actual water level, so the height, okay, in between is going to be identical for us in this particular case because it is exactly at the same depth for all of them. So this is one of the easier examples to think about, but it still will give us the actual interest, okay, and the understanding of how do we calculate a pressure. So you can see here on the first one, we do have a pressure, and that pressure is going to be caused purely, really, by the actual liquid or the fluid within this container. Notice that there's a lid, which is right up above. So if you were thinking about this, then you would have your actual pressure, which is coming from the atmosphere. So that would be trying to get in. So that pressure would be based on that lid, but it would be stopped by the lid. Now, inside, so you can see there that there is some kind of a gap. So you have some air which is inside, okay, of this container. So within here, so sure, you do have air, but the pressure which is caused down from the air on the actual fluid, so this, which I guess you can call the atmospheric pressure with regards, okay, to that, this would be negligible, and you can calculate what that pressure is. Air is not very dense at all. So if you wanted to calculate what exactly the pressure is at the point of impact when the lid is closed, it's pretty much zero. Now, just like any other fluid that you would have, you can certainly take the actual, so here you can take what the density of the air is, you can multiply it by gravity, which is G, and then you can check what the actual height is. So here I'm going to put height of the air, and what I am referring to is that would have been the height from here to here. So that's the height. And because this is so tiny, the density, right, within is so small, the height within, because that lid is closed, so inside of there, so what you would have is that the actual density, so all of this, okay, inside here, and if you wanted to calculate the pressure at that point where the H, so again, the H of air is basically this distance or this depth, this would have been pretty much, okay, we would say it is approximately 0. It's not exactly 0, but it's very, very tiny. For the illustration of all the examples you run into, as soon as you close, right, doesn't matter how much air you have within there, the pressure caused by that air, if the lid is not open, then that would be very, very small. So really, the only pressure that you would have or that you would experience in here, and you wanted to be able to calculate that pressure, would really be based on from the liquid itself at any depth. So the deeper that you go, the pressure gets larger and larger because there is more stuff on top of it. So in this case, if you wanted to find out what the pressure is, you can think about, okay, the absolute pressure at this particular point would be equal to the lid is closed. So your pressure from the atmosphere that you would have, okay, within here, so that is the air, okay, that you have right on top, basically would be pretty much 0. So the only thing that you would be reading, okay, you would just have your gauge pressure within there. And if you wanted to find out what that is, you certainly can do it by the standard equation. Whatever the density that you're talking about, if it's water, you would take the density of water. You would have to multiply it by gravity, and it would be multiplied by the height, okay, that you would have. So this is the height, and that would have been your actual gauge pressure or your pressure at that depth. Where this, the atmospheric pressure, okay, for us, because the lid is actually pretty much closed, okay, is approximately 0 in this case. You would have no other pressure. The atmospheric pressure is blocked off because of the fact that the lid is closed, and the lid is a solid, it's not a liquid. So it doesn't pass the pressure over, okay, through. It just basically blocks the pressure, right, unless it starts to cave in, okay, or something of that nature. So that is one example that you can see here in trying to find out what the pressure is. And you can certainly substitute anything that you like, okay, in terms of the fluid density. The G is always the same. It's gravity 9.8 meters per second squared. The H is always the depth that you want to be able to calculate. The deeper you go, okay, the higher the pressure becomes. Now, once you remove the lid, then you have a completely different problem. Because when you remove the lid, then the actual atmosphere, so everything around, okay, that is surrounding, is going to now be pounding on this actual fluid. So that pressure is there. It's always present that you have. And that is indeed the pressure of the atmosphere that you have. And that is certainly not going to be 0 now because you've opened it up to the actual atmosphere, to the air, okay, and it basically extends all the way through. Now, what is that atmospheric pressure that you have in here, right? So what is it, okay, that it's going to be, okay, so that pressure of the atmosphere that is coming in here? Well, so this typically kind of at sea level or, you know, very close to the earth, okay, we call this 1 atmospheric pressure, and it is equal to 101, okay, 1,325 pascals. Okay, so that is the ultimate pressure of the atmosphere that you have. So 101, and this would be 325 pascals. Sometimes it is rounded. So it's quite a lot of pressure, right? That's what you would have. And now, if you wanted to find out what the overall pressure is, so the absolute pressure, which is the summation of all of the pressures at this depth in this fluid, then that would indeed take the atmospheric pressure plus it would add the gauge pressure, and that gauge pressure would be just the difference away from the atmospheric pressure that you have, and that would be caused by the weight of the fluid itself, which indeed would be the same as in the first case. So that's still just equal to, so this would still be just the density multiplied by gravity and the height. because that height is identical. Now, of course, if you change that height, so if I brought it down and if there's less fluid, then you've changed the height, and obviously the gauge pressure at that depth changes because it's a much different change. So that's, we certainly can do. Now, if you shift over to the third example, now in this case, again, there is no lid, but now you have an actual container, which you can see there. It's about a third. But vertically, okay, it has the same height. So this is something that students have to be familiar with. It does not matter the container itself. What matters is the height away from the top. So just because of the fact that, we've basically shrunk this, so within here, but there's still the same amount, okay, of fluid up above if you're talking about pressure, because pressure is the actual force exerted over a surface area. So yes, the amount of fluid is less than it is, for example, over here, but your area, okay, proportionally also has changed. And because of that, the actual absolute pressure, so this, your absolute pressure is going to be identical as it is over here. This does not change. You still have your atmospheric pressure pounding on this, and the actual height right here has not changed. So that means that the gauge pressure that you would be reading at this particular level, this depth, again will be the same. And it doesn't matter, you can keep collapsing those walls, right? You can make a very thin, like almost like in an IV, where you have just a liquid which is striving in, okay, but it's on a very thin, but there's still liquid up above, and then the surface area you've decreased as well. So both of these have exactly the same absolute pressure and gauge pressure at that same depth, right? But this one does not have the exact same, okay, absolute pressure, because you've now covered, okay, this, and you have put a lid on top of it, so the atmospheric pressure cannot get in there. So that's what you have right there. So this does not have the same, okay, these two have the same absolute pressure. Both of these are under the atmospheric pressure because there is no lid. They have the exact same gauge pressure, okay, that you would have in here. And now this one, even though with the lid, obviously this, okay, so coming from the weight, this would have the same pressure, okay, in all of these. So this pressure, due to the weight of the fluid, doesn't matter if there's a lid or not, just based on that fluid, that would be identical. So that's what you would actually read out, okay? So all of these would be the same. So that is absolute pressure, atmospheric pressure, okay, and gauge pressure that you have. Of course, it will depend on the density. Now, of course, there are many other densities that you can deal with, right? Many different fluids that you have. Now, let's take this a step further and let's complicate this. So now I'm going to give you an example. So here's the example that I want to be able to show you. So let's imagine, right? So we've constructed this. It almost looks like a laboratory. Now notice there is no lid, okay, on this. And this is some kind of a container. And in this container, so here's the fluid. So that fluid, okay, is all the way everywhere inside. And now the question arises, okay, what is the pressure at any depth that you want to be able to read? So for instance, there is no lid on top. So if you wanted to know what the actual gauge pressure is here, so at this particular point, so what is the gauge pressure at that point? Then how would you do that? Well, the gauge pressure, right at the surface is going to be 0 because the only thing that is present is the atmospheric pressure, okay, that is pounding on this fluid from up above. So that atmospheric pressure, sure, it is present, right? But your gauge pressure, because you are not inside, okay, of the fluid, there's no depth yet. So that gauge pressure would be just 0. So your absolute pressure is just equal to the atmospheric pressure. So they're equivalent right at the surface. But as soon as you submerge yourself at any depth, this does not matter. If it's here, okay, if it's here, whatever it might be. You know from the previous example that now all of a sudden your gauge pressure changes. It will be the density that you have multiplied by the gravity and then the depth or the height away from the surface, right? So that will be present. Now, when students are thinking about this, they don't have a problem, okay, as long as they look and it's almost like it's a vertical container. But this is not just a vertical container, right? So this kind of flows, okay, well, there is no flow. Static means that it's stationary, so there's no official flow. It's not moving from a higher pressure, okay, to a lower pressure that you have. It's kind of fixed. But, okay, what really trips students up is, for instance, if you wanted to find out what the pressure is, let's say at this level right here. Now, to students, you might say, oh, well, you are at a zero height, okay, from the top of the actual fluid because you're right against, okay, the actual container's wall, at least the horizontal wall up above you. Now, that is wrong. You're not at a height of zero because in fluids, what happens is that the pressure gets transferred. So technically, so this height maps out to the same height that you would have all the way over here. And as you can see there, let's say if these were in meters, so this would be almost, you know, like if I took this as basically 1, so from here to here, okay, and then this right here looks like it's basically almost like a third. So you are submerged, okay, within here, and it has the same pressure as you do over here. So the pressure here and the pressure here are equal to each other. So, and that also comes back from thinking about Pascal's principle as well, right? That the pressures are kind of undiminished, okay, as you have within. And that's something that you should think about now, that in a fluid, if the depth is the same, now it doesn't matter, right, how this looks like. So you can literally have a container, okay, you know, that looks like this, right? So it's just kind of like squiggly up and in, and you have your actual liquid, you know, maybe this continues on downwards, so on. So at the same depth, so as you would cross this through anywhere at this point, right, on the same vertical path, at all of these points, this one, this one, this one, this one, and this one, because this is all closed in, right? So this is all closed in. You have the same fluid inside of there. That pressure is going to be identical. So at that depth, the pressure is identical. So the pressure over here is actually the same pressure as you have over here. So that is the same. And that is a very big thing that students often miss. So what does that mean? It means that if you were even going down, and it doesn't matter if it's all the way and you would cut this across all the way through, this pressure, and the pressure at the same is the same depth because it's the vertical height away from the first instance that that liquid is present. And then that pressure transfers, right, undiminished within the fluid, okay, if it's at the same depth that you have. Now, this is, of course, for static actual fluids, right? So there's no flow that you have, that this is actually moving along, right? So if you kind of would empty this and you would cut away the bottom here, then obviously that fluid would start to flow out, right, up to a certain point. And then it would just kind of go in, you would empty all of this, and then you maybe would have some fluid that's still left over here, right? But all of this would have been gone. And obviously in that case, you know, now you're dealing with a different fluid. So it would be air, okay, and then you would have something else on the left-hand side. So that's the key. At any vertical point, I want you to know that the pressure is the same. So for instance, if I asked you what the pressure is over here that you have at the bottom and over here, they are the same distance away. They're this height away from the top of the initial fluid, okay, as long as there's a continuum in the fluid that you have. So that's something that all students should take in mind. And that pressure always comes in and it is equal to, so for all of those pressures, it is always the density of that fluid, the gravity, okay, and the height that you have. Now, if you want to see where that derivation came from, I'll put up a link up above there, right? So that is the pressure at a depth within a fluid, okay? And you can see that if you wanted to. Now, don't forget that if you want the absolute pressure, right? So the absolute pressure would be the atmospheric pressure plus the pressure which is coming in from the fluid at that height. If you're just interested in the gauge pressure, then that gauge pressure is the difference away from your atmospheric pressure at any point. And that would simply be this right here. So this pressure at a height really is your gauge pressure that you would be reading. That's what you would read, okay, if you wanted to be able to see it. Now, the last component of this video, what I wanted to do is talk about, this is called the device, which is called the manometer. And for this manometer, I'll also put up some kind of references, okay, you can take a look at, okay, within the description. Now, the manometer is a device which measures out what the pressure is, okay, that you maybe want to be able to see. And this manometer initially was actually used for blood pressure, which I'll try to do a separate video on, okay, away from this. Now, for this manometer, okay, what you would have is you have basically some kind of a fluid. And now let's take a look at this. If you had a fluid, right, and this is all static, and let's say this fluid is, okay, filled up. So what's going to happen right here, now the fluid is inside, okay, all the way over here. So we know that at the same depth, doesn't matter where you are. So, you know, if it's at this depth, okay, or if it's at this depth, it doesn't matter. The pressure, the gauge pressure is always going to be the same. And in fact, you know, your overall pressures are going to be the same as well. So here, you know, pressure 1 is going to be equal to pressure number 2 on the other side, right? Now, let's imagine both of these are open. This is open, this is open. So what do you have? You have the atmospheric pressure in here, and you have the atmospheric pressure, you know, pushing this here and pushing this here. So at this instance, all you have, because you have not kind of dove into the actual fluid, so those are going to be just the atmospheric pressure. They're going to balance off, and you're going to have a nice same line. But now let's imagine that you're going to be closing this thing in. So now, you know, you close this thing in, okay, and now, so as you close this in, okay, maybe there's some pressure which is coming in from here, right? So this is attached, okay, to some kind of a device or something else. So basically it's all closed in. So let's imagine that. So I'm going to kind of just draw it out in here just so that, you know, it replicates for us that, you know, there's some kind of a closure. So, you know, I'm going to kind of do it like this. You know, let's imagine that over here, it's some kind of a device or something else. And this is now pushing the pressure. So there is some pressure. Now, it's not necessarily the atmospheric pressure. There's some pressure, okay, which pushes in. Now, we want to be able to figure out what that pressure is. Now, if your fluid stays the same, right, then that pressure is basically negligible and it's pretty much zero. But if the pressure, right, and now if you're thinking about if this is going to be the gauge pressure, so if that pressure, okay, is now all of a sudden, okay, as it starts to get bigger and bigger, then what's going to happen is that it's going to push on that liquid. And what you will have is that all of a sudden, okay, these lines that you see, this liquid now all of a sudden will get pushed up, and then this will get pushed down. And now you might be scratching your head, okay, and you're saying, ooh, okay, so that's interesting. What has happened? The liquid itself, you have your atmospheric pressure, which is pushing this down. On the other side, you have whatever pressure you want to figure out is over here, right? So what is that pressure? And you want to be able to think in terms of fluids. How would we solve this? And this is how the manometer is used to be able to find out what this pressure is. Now, please keep in mind, so whatever it is in here, so whatever that pressure, we're assuming that it's coming from a fluid. So typically it might be air, which is now trying to get compressed down, okay, from whatever device it is. hint, like for instance, reading a heart kind of pressure, okay? So your blood pressure that you have. So let me break this down to you. How would you try to attempt to solve this? So first of all, what do we know? We know that the pressure in fluids at the same depth is identical. So that means that the pressure here and the pressure here, because they're both fluids, must be the same. Now we know that in here, the only pressure is that P. So on that right-hand side, so the right-hand side over here, all I have is this pressure P. Now on the left-hand side, what do I have? Well, so if I think about this, then I have, so I'm going to kind of just draw a line over here, and I'm going to designate that, hey, wait a minute, I have a certain amount of liquid here. At this pressure, so that particular pressure that I have is going to be composed of the atmospheric pressure, right, which is coming from here. So this is going to be the atmospheric pressure, which is present, plus the pressure which is coming from the actual liquid, okay, up above. Now we can calculate that, that's not a big deal. So this right here, so the pressure coming from that liquid is just simply the actual liquid itself or the fluid itself. So that would have been the density that we have multiplied by the gravity times whatever height this might be or depth. And this, okay, is going to be the total pressure present at that point. So at this point, that's the pressure. The pressure is from the atmosphere plus the pressure from the actual fluid. Now, within here on the right-hand side, as I said, all we have on the right-hand side is just the pressure coming in from that device. And that is equal to, okay, this P. But now, if you look at this equation, so P atmospheric, right? So the atmospheric pressure plus, okay, this right here is equal to the pressure on the right-hand side. This looks like our equation for the absolute pressure that we would have. So this is exactly like this that we have in here, where that absolute pressure is indeed the absolute pressure which is being kind of present there for us. So if you wanted to find out what the gauge pressure is, what the difference is, and then whatever this device, whatever that pressure is, okay, over here, well, then that pressure is going to be read out, and this is your gauge pressure that you have. That's the extra pressure that you have, which is going to be pushing that liquid up. So it's no longer balanced because it's pushed it up. So that means you had extra pressure on the right-hand side. That extra pressure is coming from wherever it might be, and it pushes the liquid up, okay, and then pushes this one down. And the difference in between is how the manometer actually reads out what the overall pressure is. And this is when this is called the positive pressure, because it's positive, right, as it pushes it on. Now you can have another instance, right, in exactly the same place. Now think about, sucking away air or sucking away. So you can certainly have pressure, and the gauge pressure up above in the example would be positive. But here you may have the gauge pressure which might be negative. Now, you might scratch your head and you might say, so what's going to happen, okay, in here? Where, you might have this pressure, okay, which is kind of trying to, push or pull this along. And what you observe is now something different. You might observe something like this happening, where the liquid gets pushed, okay, up on the right-hand side, right? So on the right-hand side, so what you would say is, okay, well, so I do have my atmospheric pressure, which is pushing this, and somehow, okay, the atmospheric pressure within here has allowed this to go up. Now, if it's going up, that means you might have negative. So this would be negative pressure in here, so negative gauge pressure. You can think of, suction cups or something like this, right? Where you want to be able to pull something up and you want to know what that pressure is. The negative just means that the gauge pressure, right, is going to be, so the overall item is going to be less than the atmospheric pressure, which is pushing it down. And now how would you actually compute it? So unlike the previous example, notice we started from the right, we cannot start here, okay, and do this. What we must start is you always start at the base where the liquid is, okay, so within here. So you would start it like this. And now all you have on the left-hand side, so on the left-hand side over here, all you have is the atmospheric pressure. And on the right-hand side, so this would be on the others, right? So that again, we want to measure it at the same depth. So this right here, the same depth. So we want to know what the pressure is here. Well, the pressure over here is going to be whatever, okay, we had. So within here, so this is how I like to look at it. This is the pressure there plus, okay, whatever is coming up, okay, along within here. And that would be, again, just the density, right? And that density is G, okay, multiplied by whatever height this might be. And now notice, if you wanted to figure out what this P is, right? So this P right here, which is being kind of, well, we know that it's going to be sucking it away. So it's the negative, right? Before it was pushing it, so it pushed the liquid up. Now it's sucking it away, so it's actually grabbing, okay, or forcing the liquid back up, okay, in the opposite direction. So if you want to know for that P, you can certainly take this term, you can bring it to the other side, and what you're going to get is you're going to get your P atmospheric minus, okay, this right here, and it is equal to that overall pressure there. So that overall pressure, as you can see, if you're thinking about the gauge pressure, then this is your gauge pressure. Notice it's negative. That means it's less than the atmospheric pressure, right? So that P, right, because of the fact that it's now sucking it away, so it has to be less because now it forces that pressure, the atmospheric pressure, to push down more, and then the liquid will rise. So if you were reading it on your gauge or on your manometer, okay, which this thing is used, then what you would find is you would find a negative value in this way. And you can think about either above, as the pressure pushes down and it is bigger than your atmospheric pressure, then the liquid will rise on the left. But if you're sucking away and the pressure is less, the overall pressure is less, then the liquid's going to rise up, okay, on the right-hand side and not on the left-hand side. So you will find a positive and a negative pressure, right? So this is what you would have. And here, the one that I'm leaving you with at the end, this one, okay, is the one which is most commonly used to try to figure out, okay, what your heart blood pressure is, okay? And, you know, it is utilized within, and it was originally used within this device, which is called a manometer. So I hope that this video gave you several examples. Now, I didn't provide you any calculation examples within. It was more of an intuition into trying to understand how you can figure out pressures at the different depths, and then how can you think about it. The key is that at the same depth for fluids, the pressure must be equal to each other. And if that pressure is equal to each other, then you can come up with these actual equations to figure out what the gauge pressures are. You can figure out in harder, you know, kind of weird looking devices what the pressure is at any depth. Just please don't forget, if it's a continuous flow and it's not cut off anywhere, okay, then, you know, those pressures actually change. Now, if I threw a wrench at you, so here's a wrench, if I put, okay, and if there was a slid that I could block this off, right? So I could block the left-hand side from the right-hand side. Now all of a sudden, that blockage, right, that you have done is going to now change the actual pressure, overall pressure. Because now assuming that that lid, okay, is not passing in the pressure from left to right. So if you block it off or if you remove it, now it's a different story. Now the right-hand side would start from here. This is the top. The left-hand side, the top is over here. But as soon as you remove this lid, now it's a continuous flow, and there's only one top, which is on the left-hand side. All right, so thank you for watching. Okay, I hope that you have found this useful. See you in future videos. Bye, everybody.